We're going to talk about a math problem today that is so simple a kid can get it, but it's stumped the smartest people on the planet for decades. It's called the Collatz Conjecture. But what if the answer wasn't buried in some impossibly complex equation? What if it's been staring us in the face this whole time?
I mean, really think about that. For almost 100 years, mathematicians have been on this epic hunt for a crazy, complicated proof. But what if they've been searching in the wrong place entirely? Because they just misunderstood the question itself. Let's dig in. All right, so first things first, what is this thing? It's famously called the simplest unsolved problem, and for good reason. The rules are, like, shockingly easy to understand, and yet, with all the power of modern mathematics, nobody's cracked it. It's a total enigma.
Okay, here are the rules. You ready? Pick any whole number you want. If it's an even number, you just cut it in half. If it's odd, you multiply it by 3 and then add 1. That's it. And the big idea, the conjecture, is that no matter what number you start with, big, small, whatever, you will always eventually fall down to the number 1.
So let's try one. Let's start with 7. Well, 7 is odd, right? So 3 times 7 is 21, plus 1 is 22. Okay, now we have 22. That's even, so we divide by 2, and we get 11. Now we're at 11, which is odd, so 3 times 11 plus 1 is 34. You see how the numbers just bounce up and down? But eventually, it seems like they all get sucked into this little loop at the end. 4 goes to 2, 2 goes to 1, and then it just repeats forever.
And trust me, people have tested this. I mean, they've really tested it. Computers have been crunching numbers for years, checking every single integer up to an absolutely mind-boggling scale. We're talking numbers in the quintillions. And in all that searching, not one single number has ever been found that doesn't lead back to 1. Not one. And yet, there's still no proof.
And this is where things get really interesting. See, this is where our story takes a sharp turn. Let's bring in Edward Gomez. He's not a traditional mathematician. He's a systems developer. So for decades, his job was to work not just with our normal decimal numbers, but with the systems computers use, things like binary and hexadecimal. And that background, well, it gave him a totally different way of looking at this, a perspective that almost everyone else had missed.
So here it is. This is the core of Gomez's whole argument. He says we've all overlooked the most basic thing, the rule itself. The rule is written down using our decimal symbols. The moment you write 3n plus 1, you're not just playing with abstract numbers anymore. You're locking the entire problem inside our specific, human-made system of 10 digits, from 0 to 9.
Now, to really get this, we have to make a distinction that is, well, it's absolutely crucial, but it's something we forget about all the time. We have to separate the idea of a number, its value, from the symbol we use to write it down.
So think about it like this. The value is the pure abstract idea, the actual concept of 3 things, like 3 apples on a table. But a symbol, like the character 3, that's just the squiggle we all agreed on to represent that idea. They're not the same thing.
And you can see it right here. The value of 10 is just 10. It's universal. But in our everyday decimal system, we write it as 10. A computer in binary writes it as 1010. In hexadecimal, which is used all over in programming, it's just the letter A. The value underneath is identical, but the symbols and the rules for how they work are totally different systems.
And that brings us to the big punchline. The conjecture is written using the symbols 3 and 1. It doesn't say take the abstract value of 3. No, it uses the specific characters from our decimal system. And according to Gomez, that one tiny overlooked detail, well, that's the key to the whole puzzle.
Okay, so if the problem is really trapped inside our decimal system, what does that actually mean? What does it mean for the search for some weird number that breaks the rule? Well, it means we might be looking for something that the system itself, by its very design, can't even create.
Think about it this way. The entire infinite universe of numbers, every single one, gets judged by one tiny thing, its very last digit. That single symbol, which can only ever be one of just 10 characters, is what decides if a number is odd or even. The rule doesn't care how big the number is. It only cares which of those 2 little groups its final digit belongs to.
And if the very next step is always decided by a finite, predictable set of symbols, then the whole system is closed. Its behavior is contained. There are no escape hatches. There are no secret backdoors, because the rules are based on the symbols themselves, not some abstract math property that could exist outside the system.
A really good way to get your head around this is the Lun algorithm.
That's the formula that's used to check if a credit card number is valid. You can start with this huge 16-digit number, run it through this process, and it always boils down to a single check digit between 0 and 9.
And here's the thing, nobody out there is wasting their time looking for a credit card that produces a check digit of 14 or, I don't know, the letter Q. Why not? Because we all understand that the structure of the system makes that impossible. The system is built to only spit out a single digit from 0 to 9. The outcome is basically guaranteed by the rules of the game.
Gomez has this perfect analogy for it. He says searching for a Collatz counterexample is like making chicken soup. You're in a system that only contains chickens, right? And you just keep adding more and more chickens, testing bigger and bigger numbers, hoping that eventually one of them is going to taste like beef. It's never going to happen. The fundamental ingredients of this system just don't allow for it.
So if we actually accept this idea that the system is closed and the search is kind of pointless, it forces us to completely reframe the entire mystery. It means maybe we've been asking the wrong question for almost 100 years.
See, the real mystery isn't trying to prove that every number eventually falls down to 1. That's what everyone's been obsessed with. But maybe that's like looking through the wrong end of a telescope.
The real question is this. Given that the rules are defined inside this closed, deterministic symbolic system, why on earth would we expect any number to be able to break those rules? Suddenly, the burden of proof completely shifts. The surprise isn't that they all follow the path. The real surprise would be if one of them didn't.
Now look, this isn't a formal mathematical proof in the traditional sense. It's a structural argument. It's about the nature of the system itself. And what it suggests is that while mathematicians have been searching the heavens for some complex answer, it might have been hiding right here on the page the whole time, encoded in the very digits we use to write the problem down. So the question for you is the answer really out there, or is it right here in the digits?